All right, so what I wanted to do today is do some more examples out of section 2.3, do some more examples where we have some repeated roots, do some more examples where we have some complex roots. We didn't get a lot of those in yesterday, so we'll do some more examples of that. Okay, so let's say we had the fourth derivative minus 6y times the third derivative plus 9y second derivative equals 0. How do you solve that differential equation? You start by writing the characteristic polynomial, which is simply r to the fourth minus 6r cubed plus 9r squared equals 0. And then you have to be able to factor that polynomial. Can you factor that polynomial? Well, you don't want to divide by anything. You want to factor by something. So what can I factor out? I can factor out an r squared. How come you don't want to divide by anything? Then you lose roots. You don't have them that you need them. So we have an r squared times r squared minus 6r plus 9. That's r squared. Can you factor r squared minus 6r plus 9? Yes, it factors as r minus 3 and r minus 3 again, right? So what are the roots of the characteristic polynomial? R equals 0 and r equals 3. That's it. There's only two roots. All right, so my next question is, we started with a fourth degree polynomial. Aren't there supposed to be 4 roots? No, there's no imaginary this time. There are repeated roots. For example, r equals 3 and r equals 3 shows up twice. So 3 is a repeated root. 3 really shows up twice. And 0 is also a repeated root, isn't it? But it's a repeated root. It's 0 and 0 shows up twice, right? Because I can write that as r times r. So I actually have 2 repeated roots here. 0 is repeated twice, and 3 is repeated twice. So I do have 4 roots. It's just that they're not all 4 distinct. I've got 2 zeros and two 3s. All right, so what does it mean? I don't think we've had one like this yet. What does it mean for r equals 0 to be a root? What's one of the solutions going to look like? Just a constant, because we would have c1 e to the rx, but r would be 0. E to the 0 is always 1. So we're going to have our general solution is going to be y equals c1, and then we would have e to the 0, which is just 1, plus, now since r equals 0 is a repeated root, what has to happen? You have to have a c2 times x. Because it's repeating. Every time it repeats, you multiply by an x. So if this were an r cubed, I would have a c1, I'd have a c2x, and I'd have a c3x squared. Because it repeats 3 times. I would need 3 terms for that one. All right, so that takes care of the r equals 0 with having the fancy math words are r equals 0 has multiplicity 2, which means it shows up as a root twice. Plus, all right, so now we have r equals 3 as a root. So what does one of our solutions have to be? C3e to the 3x. And once again, r equals 3 has multiplicity 2. So we need another one that involves e to the 3x. So we're going to have a c4 x e to the 3x. There would be our general solution to that equation. Questions on that? That gives you a better understanding of how those repeated roots work.
C2x is...
This one came from C1 was really C1 e to the 0x, because r was 0. But e to the 0 is 1. And then C2 was really C2 x e to the 0x. Those two both came from the r equals 0. But e to the 0 in both those cases is 1. And then we had the C3 e to the 3x. And then again the repeat, so we needed to multiply that one by an x. So that we have 4 linearly independent solutions. Okay, good. All right, how about y double prime plus 5y prime plus 5 equals 0. R squared plus 5r. Oops, that should have been a 5y right there, by the way. Y double prime plus 5y prime plus 5y equals 0. R squared plus 5r plus 5 equals 0. Can you factor that quadratic equation? No, I can't. So what do? I pull out the calculator. And I push the program button, and I have a nice program for the quadratic formula. If you do not have a nice program for the quadratic formula, you should see me after class, and I will give you a nice program for the quadratic formula. And you want mine, rather than the one you might have on your calculator if you don't have mine, because mine will also give you complex answers. And you need complex answers in this course. 1, 5, and 5. Oops. A is 1, B is 5, C is 5. It turns out this one does not have complex solutions. The solutions are negative 5 plus and minus square root of 5 over 2. All right, so R equals negative 5 plus or minus the square root of 5 over 2. Not very nice answers. It's okay. What's the general solution? Y equals C1 e to the one of those answers, that's right. Negative 5 plus the square root of 5 over 2 times x plus, oops, I think I said square root of 5, but I wrote square root of 2, plus C2 e to the other one. Negative 5 minus square root of 5 over 2 all times x. There's your answer. So those R numbers don't need to be nice numbers. They can be ugly numbers also. Questions on that?
If you were to reduce that down to just like the actual negative 1.38.
Personally, my opinion is I would prefer not to round off. And the reason is, especially when you're dealing with exponential functions tend to grow really, really fast. So if you round off here and then you plug in a relatively big number for x, even like 10 or 15, you're going to incur a lot of round off error right there. So I would keep it as exact for as long as you can. That would be my opinion. If you were doing this on a quiz or a test and you gave me negative 1.38, I probably wouldn't mark it wrong. But in practice, it's better to keep it as exact as long as you can.
If your calculator doesn't use that,
then you get a better program. If your quadratic formula does not give you exact answers, get a better program. So see me after class and I'll give you a better program. All right, let's see if I can find one that does have complex answers. How about 6y fourth derivative plus 11y double prime plus 4y equals 0. All right, so we know how to start. Starting is really easy. 6r to the fourth plus 11r squared plus 4 equals 0. Wonderful. Now what? Plug it into the calculator. All right. Y equals 6x to the 4th plus 11x squared plus 4. Draw me a picture. I got a real problem. I've got a little thing here. I can see the graph. What's the thing that's got me worried? I don't see any real roots. Uh-oh. What do you do?
No real roots.
No real roots, which means there are 4 complex roots. And we know how to handle complex solutions now, in theory.
Practice, yeah.
And not so much in practice. What do you do? All right, well, let's see. Even though there aren't real roots, can we factor this? How can we get 6r to the 4th to show up in the front? It could be 3r squared and 2r squared, or 6 and 1. We got to take a guess. Let's try 3 and 2. 3r squared, 2r squared. How can we get 4 on the other end? 2 and 2, or 4 and 1? I'm going to try 4 and 1, just like that. And if I do a quick FOIL, I would notice on the outside I have 3r squared. On the inside I have 8r squared, and that happens to add up to 11r squared. Lucky guessing, huh?
Yeah.
Do you believe in junkyard factoring?
Yes, I believe I will mark it wrong. There is no such thing as junkyard factoring.
Okay.
I believe it.
Don't worry about it. It's wrong. You don't do it. We can't talk about that in this class. We will not talk about junkyard factoring in this class. All right. Well, now the good news is, now that we have this factored, now we have little quadratic equations, and we can solve little quadratic equations, can't we? So this one would be 3r squared plus 4 equals 0, which means r squared would be negative 4/3. So r would be plus and minus I times 2 over the square root of 3. And then we can do the same thing with the other one. 2r squared plus 1 equals 0. That's r squared equals negative 1/2. So r would be I plus and minus I square root of 1/2.
Can you go over how you went from r squared equals -4 to the r equals plus minus I?
I took the square root of both sides. Right there, you mean?
Yeah.
So I took the square root of both sides. And when we do square roots, of course, there's always 2 of them, a plus and a minus.
Okay.
And then since there's a negative under my square root, that tells me I'm going to get an I.
Okay.
And then the square root of 4 is a number 2.
Okay.
And the square root of 3 is not a nice number, so I just left it as square root of 3. You haven't seen eyes in a long time. All right, that happens. Okay, so remember, if we had, according to our good friend Euler, if we had something in the form of a plus bi, e to the a plus bi, and we'll even put an x there, because this is what we want our answer to look like, we were going to end up with an e to the ax, and then we were going to end up with a c1 cosine of bx plus c2 sine of bx. Where those c1s and those c2s, they could end up being complex numbers. We were okay with that. So let's look at our complex numbers here. For this complex number, what's the a value? A is 0 because there's no real number sitting out front here. A is just 0. So we're not going to have an e to the ax because our e to the 0 would be 1. So our b here is 2 over the square root of 3. So our solution is going to look like y equals, we're going to have c1 cosine 2 over square root of 3x plus c2 sine 2 over square root of 3x. So there's 2 of our answers. How many more do we need? 2 more. But we've got the same thing over here, don't we? What's the real number sitting out front here? It's 0. So again, our a to the 0, or e to the 0, I mean, is just going to be the number 1. Then we're going to have a sine and a cosine with that b number. So plus c3 cosine square root of a half x plus c4 sine square root of a half x. There's our 4 solutions. Questions on that? All right, here's the last thing I want to do in section 2.3. We're going to play Jeopardy. So now I'm going to give you the answer. There's the answer. The answer is y equals c1 e to the 4x plus c2 e to the negative 2x. And I want you to tell me what was the differential equation that solution came from.
We know our 2 r's are 4 and -2.
So we know that r equals 4 and r equals negative 2. Absolutely. So what does that tell you? It's a second order equation because there are 2 answers. That's good. What else does it tell you? You had to have, not x, r, but you had to have an r minus 4 times r plus 2 equals 0. That had to be your characteristic polynomial. FOIL it out. That's r squared minus 2r minus 8 equals 0 when you FOIL it out. Which tells you your original differential equation was y double prime minus 2y prime minus 8y is 0. Questions on that?
Nope. How hard do you make it?
Oh, how hard am I going to make them? Oh, that was the easy one. That's right. That was the warm-up. So what if the solution is y equals c1 e to the 3x plus c2 x e to the 3x plus c4 cosine 2x plus c3 sine 2x. Apparently I can't go in order with my c's, but that's okay. C1, C2, C4, C3, the order of the C's really doesn't matter.
That tells us
So what does that tell you? What does the e to the 3x tell you?
the r's
You have r equals 3. And then the c2x e to the 3x tells you have r equals 3 twice, don't you? Which means in your characteristic polynomial, you had to have an r minus 3 squared.
And for the cosine and sine, it shouldn't be plus or minus 2i.
So this tells you you had r equals plus and minus 2i.
Because a is 0, that's why it's not there.
Because, right, there's no e to the 0 out here. There's no e to the thing out here, so a is 0. So if r equals plus and minus 2i, what did that have to look like from the original polynomial?
R squared is
Close. R squared equals negative 4. 2 squared is 4. Which means you had to have an r squared plus 4. Correct? If I square both sides here, r squared is r squared. When I square 2i, 2 squared is 4. I squared is negative 1. And then I move the negative 4 over, it becomes a plus 4. So there's what my characteristic polynomial had to look like when I factored it out. It had to be r minus 3 squared times r squared plus 4. Now what I have to do is I just have to FOIL the whole thing out and then write everything using my y primes. R minus 3 squared, that's r squared minus 6r plus 9. And then I have to multiply by the r squared plus 4. So that's going to be r to the 4th plus 4r squared minus 6r cubed minus 24r plus 9r squared plus 36 equals 0. So the original differential equation must have been 4th derivative of y, and then my r cubes, there's only one of those, so minus 6y triple prime. My r squareds, I got a 4 and a 9, that's 13. So that's a 13y double prime. Only one r, it's right there, so that's a minus 24y prime. Plus the only number is 36y equals 0. There's the original differential equation. Questions on that? Well, the obvious question is, other than that being a fun game, why would I make you do that?
It's kind of cool.
It is kind of cool that you can go backward, that you can start from the answer and tell me what the differential equation had to be.
You can derive something, but you always able to go back.
True, if you can derive something, you should be able to go back and get the original, but that's not really why I had to do it. The reason is, in the very near future, a couple sections from now, we'll start learning how to solve non-homogeneous equations. What makes it a non-homogeneous equation? It doesn't have a 0 here, it has something else. This going backward technique will be the whole key to solving non-homogeneous equations. This is exactly what we'll have to do to solve the non-homogeneous, and we'll see that when we get there. So that's why we do it here. We start practicing here so that when we get to that, you're familiar with how to do that technique already. Questions on that?